it's important to know, just like in nucleophilic displacement, the hydrogen should be what's called anti-periplasmic. To the living group. If base picks up the hydrogen that is on the same side of the living group, the elimination will not take place. There's a sigma star at the back, pointing 180 degrees away.
I'll give you the pages.
All the electrons should go into this sigma star. Okay? Yes?
Can I do it here? Or just only one? Just start this. I'll give you the pages after.
This one. So this will not happen. So it is not happening because there isn't right here. There is an overlap. There is an overlap between sigma star and sigma CH. And when this base comes and picks it up, that is facilitating the deprotonation.
Reactions.
Okay? The base will simply not pick this up because there is no overlap. There is nowhere for these electrons to go.
Just like a normal one. You're just saying which way the electrons flow. It's not a big deal.
It's a big deal, I guess.
Are you okay?
Okay? We'll get back to that. I will discuss that several times during today's lecture. But we're going to see it, the reason I'm getting with that is we're going to see it over and over again throughout the lecture. Now, what happens with the acid-cat-like elimination? In the acid-cat-like elimination, what you have is you have an acid. The mechanism is different. You have a tertiary alcohol. You have a very strong acid. Remember when I told you OH is not a good living group. To convert it into a better living group, you have to protonate it.
Mm-hmm.
So the first step is protonation. Second step is elimination. Water leaves. And the reason for that is we can form stable tertiary carbocation. And then, what happens with this? What is the difference between just carbocation and the living group? Carbocation has empty p orbital. It doesn't care whether the electrons go from the bottom or from the top. So this is all carbocation. This is empty p orbital. It's empty from both sides. Hydrogen here, hydrogen here. Any hydrogen will do. If hydrogen from the bottom will be picked up, it will bring its 2 sigma electrons to the bottom and the double bond before. Exactly the same outcome if hydrogen from the top will be picked up. It will bring its 2 electrons to the top. And the result Okay? So two distinct mechanisms. One is elimination. Second is elimination of the living group. Second is elimination plus stable carbon. And in this case, it doesn't really matter which hydrogen is picked up. Okay? So again, we'll get back to that. Yes. We'll get back to that several times. Okay. So now you're familiar with all that. This is a quick review. We've seen this reaction many times. This reaction follows which rule? Markovnikov's rule. Okay. Again, I'm just trying to emphasize the importance of putting acid as well as the solvent. So, for example, in this particular reaction, if you were to put water, then the outcome of this reaction will be very much different. So the reaction follows Markovnikov's rule. Protonation first of the carbon with most hydrogen, tertiary carbocation, and then bromide will attack. So this is a non-Markovnikov's product, which will not form, because the protonation is always at this site to form the most stable tertiary carbocation. So this reaction is achiral because, again, when the carbocation is formed, empty p orbital, bromide can come from the top, can come from the bottom. When both carbocations have similar stability, then there will be no differentiation, of course. Any one will work. So first you can imagine these two products will arise from the protonation at this position, and carbocation is formed right here. So bromide can come, and then it will attach. This is from the top phase, and this particular group again. You see, you can get protonation from the top, from the bottom, sorry. You can get protonation from the top. Bromide, in both cases, attacks from the top. The same story, you can get protonation from the top, you can get protonation from the bottom, and bromide, in this case, attacks from the bottom. So this is just an array of products you can form in this particular reaction. And I hope if you understand why it may look like a complex picture, but if you understand the protonation and subsequent addition to the carbocation, then it's pretty much obvious. Then again, this carbon may pick up a proton from the top, and bromide can attack from the bottom or from the top. Now, protonation may occur from the bottom plate, and bromide can come from the top or from the bottom. Okay? So quite a few outcomes for this reaction. And again, are there any questions? Did you familiarize yourself with the protonation process? I think we've seen that a fair amount of times right now. So basically, if you do this reaction in real life, you're going to get this mess, essentially, of products, and there's nothing you can do. If you want just this one, there's no way to separate it from all that. Yeah, so this is just, we've discussed that again. Once we protonate, this is empty p orbital, attack can come from top, from the bottom. And the same story if we protonate from the other side. So this is a review of yesterday's lecture.